Hi guys, my name is Vinay Jain and today we're going to be discussing Leetcode question 111, minimum depth of binary tree. So the question is, given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Again, the nearest leaf node. And what is a leaf node? A leaf node is a node with no children. So how are we going to solve this question? So first let's understand this question by a small example. So let's say this is the binary tree that we have, with this being the root, 15 and 7. So our aim is to find the minimum depth of binary tree, that is our distance from the root to the nearest leaf node. So what are the leaf nodes here? This is the leaf node, this is a leaf node, this is a leaf node. Why? Because they do not have any child nodes, so therefore they are a leaf node. Notice that this has a depth of 2 and this has a depth of 1. So what is the minimum depth? This has a depth of, let's say, 1, 2 and 3. So this has a depth of 3. This also has a depth of 3 because this is at level 1, level 2 and level 3. This is at level 2, right? So what is the depth for this? The depth for this is 2. So what is the minimum depth? Minimum depth is 2. So how can we find the minimum depth? Our aim is not to find the depth but the minimum depth. So if we traverse every level in the tree and find if this level has any leaf node, no, then move to the next level. Does this level have any leaf node? If, for example, this side doesn't have any leaf node, right? So we check for the next nodes in the level. If we encounter a node with leaf, which is a leaf node, so that means we have found the minimum depth, because we then do not have to check the next depth, because the depth before that, the earliest depth that we could find, which has a leaf node, will be our answer. So this is essentially what we have to do, and since we have to work level by level, so we'll be using a modified version of breadth first search algorithm. So again, let's assume that this is our example: 3, 9, 20, 15 and 7, and this is our root node of the tree. So again, as we proceed in breadth first search algorithm, we have a queue and we have a pop node. So our queue looks something like this. So our first step would be to insert the root node of the tree into the queue, which is this. I'll use a different color for easy visualization. So this is from where we start, and we'll be using some variables like minimum depth, current size of queue. So we'll be using these two variables. So minimum depth initially, since this is at depth 1, this is at depth 2, depth 3, right? So whenever we insert the root node, the initial minimum depth would always be 1. And the current size of queue again would obviously be 1, but we won't compute this right now. First, this is our initialization step, and when we have inserted into the queue, then we calculate the queue size using queue.size function, which gives us 1, and we'll assign this value to this. Now as long as we have a current size of queue greater than 0, then we loop in the queue for the number of nodes that are present in the queue. We pop the topmost element in the queue, assign that to pop node, and decrement the current size of queue, because now we have worked with this, right? So this essentially now becomes 0. Now this becomes 0. We check whether the current pop node has any child nodes or not. It has child nodes, right? 9 and 20. So we add these child nodes to the queue. We add the child node 9 to the queue. We add the child node 20 to the queue. Once we have done this, we check, does this have any more children nodes? No, it doesn't. So that means, does it have any leaf node as of now? No, it doesn't have any leaf node, right? We haven't encountered any leaf node yet. So we move to the next level to check whether there are any leaf nodes in the next level. And since we have moved to the next level, now the minimum depth changes from 1 to 2 because we have increased one level, right? So this now is increased by 1. So 1 plus 1 is 2. We again go inside the queue. When we have added these elements, we check again what is the current size of the queue. So the current size of the queue is 2. So we assign this value 2. And as long as current size of queue is greater than 0, as long as there are elements in the queue, we again pop the element in the queue, topmost part, assign it to pop node, check if it's a leaf node or not. If it's a leaf node, then we return our minimum depth, signifying that we have reached a leaf node and hence our minimum depth is found. But since this is not a leaf node, we add is children to the queue. What are the child nodes of 9, 15 and 7? We add these to the queue and decrement the current size of queue by 1 because we had initially 2 nodes, right? These were the 2 nodes and we have explored 1 node out of them. So the number of nodes left to explore is 1. Then again we pop the node from the queue. The topmost node is 20, so we pop that node and we check whether this is a leaf node or not. This is a leaf node because it doesn't have any child node. So therefore that means we have reached a level where we have found a leaf node. That means we've reached our minimum depth criteria, which is 2 here in this case. So therefore we return this value. So this is the essential algorithm for this question. A more detailed version of the algorithm is somewhat like this. Again, this is an extension of breadth first search algorithm. So we initialize empty queue and add root node to it. This is our beginning step, and we assign min depth is equals to 1 because we start with min depth is equals to 1. Why? Because this is essentially minimum depth 1, this is depth 2, this is depth 3, 4, 5, so on and so forth. Now while queue is not empty, while there are some nodes to be explored, this is essentially the beginning of our breadth first search algorithm. We get the size of the queue. How many nodes are there in the queue? This essentially means nodes at current level in tree. So this essentially would give you the number of nodes at the current level, and while current size is greater than 0, while the size is greater than 0, we pop the node from the queue, whatever the node is at the top of the queue, we pop that. We check whether it's a leaf node or not, because if it is a leaf node, that means we have reached our minimum depth criteria and we return it. But if it is not a leaf node, then we check whether it has any children or not, because we have to move to the next node, right? So if it has any children, add them to the queue to facilitate our breadth first search algorithm to the next step, and decrement current size by 1 because we have explored 1 node out of the total number of nodes at current level. So we decrement the current size by 1, and we keep doing this as long as we have not explored all the nodes at the current level. Once we have done that and we still haven't encountered this condition here, a leaf node condition, that means there is no leaf node at the current level and we haven't reached our minimum depth criteria. So we need to check the next level. So for example, if we are at this level, we haven't found any leaf node, right? So we need to move to the next level and therefore increase our minimum depth by a count of 1. So whatever it was earlier, we increment the count of that by 1. So now we're working with minimum depth 2. So we increment minimum depth by 1, and then again, while queue is not empty, we keep on working with this, get the current size of the queue. As long as there are items in the queue, we keep working with it until and unless we find a leaf node. Once we find a leaf node, that means we have found our minimum depth. And for the sake of the algorithm, at the end of the part, we'll always have a leaf node because every tree needs to have a leaf node. So this condition will one way or another be encountered. But you can also add a return minimum depth condition in the end, because you have to return some kind of value from the function. That is why this condition is there. So this is essentially the algorithm for this question. I hope this algorithm helped you understand how to solve this question and how breadth first search can be used to find the minimum depth in the binary tree. I hope this video helped you explain your concepts. Kindly let me know your comments and feedback in the comment section below. I'll attach the necessary link for my GitHub repository in the comment section below. Thank you for watching this video, guys, and have a nice day.